Our presentation is entitled End-to-End OCR, so Optical Character Recognition Engine for Water Meter Readings. It was developed by my colleagues Sergio Castillo and myself in collaboration with the NRB group. As you will see, our talk will be structured as follows. First, I will give you a very high-level overview of the entire model. Then my colleague Sergio is going to delve deeper into the model itself and speak about the architecture, the data, and a bit on the evaluation. Then we will move to the results, including quantitative results, qualitative analysis, as well as portability analysis before concluding. Right, so the problem that we are trying to address is that of developing an AI-based solution which could automatically extract information from water meters. That is, it could automatically recognize digits that are within your water meters, and that regardless of the type or the shape of the water meters that you have. Then this application should be able to work offline, that is, it should not be a cloud-based service, and it should distinguish between the integer part of a number as well as the fractional part of the number. And finally, this application should be easily portable to mobile devices, which entails that this application had to have a very low memory footprint. And as you can imagine, developing AI or machine learning techniques with a low memory footprint is not always feasible or is challenging. The diagram that you see on the bottom part of the slide gives you an overall picture of the entire process that we adopted. On the left-hand side, you would see that we have a data set of water meter readings, and my colleague will give you examples of those readings later. Then those readings, they are passed through an ROI detector. Remember that word well, ROI, it means region of interest, because my colleague Sergio will emphasize a lot about it later on. And this ROI detector simply aims at detecting the portion of the images corresponding to the digits. After that step, we have a stage of manual cropping, which operates on a mask. A mask is simply an array or a vector of 0 or 1s, which have been obtained from the ROI detector. In cropping, we perform, for example, rotation to adjust the images properly. And then after cropping, we obtain a counter, which is a sequence of digits. And we use those sequence of digits to train a machine learning algorithm such that it is later able to recognize digits by itself in an autonomous fashion. Now that I have given you a very broad overview of the entire steps that have been involved, my colleague Sergio will take the lead and explain to you the detailed implementation. Sergio, the floor is yours, and obviously I will intervene whenever needed to clarify things. Thank you.
All right, thank you, Professor. Good afternoon, everybody. I will continue talking about the model architecture that we develop. Overall, in this project, we developed 3 different models. Region of interest detector that finds or detects the counter area, and the sequence predictors that takes this counter area and produce a sequence prediction. All the models were developed using Python with the well-known library TensorFlow. As we are dealing with images, all the models make use of convolutional layers. So the first model I'm going to talk about is the region of interest detector model. It is based on the UNet architecture developed by Ron Berger. It's basically a combination of a downsampling path and an upsampling path, where the downsampling works as a feature extractor, and the upsampling tries to reconstruct the image that we are interested in this case, the mask. In the original paper, the researchers were using max pooling and upsampling layers, but in this case, we decided to focus on convolutional layers with strides, so that the dimensionality operation is changed to a learnable process. This image segmentation model outputs mask of size 720 by 720. Now, the sequence predictors. These models follow the encoder-decoder structure, where basically the encoder works as again a feature extractor, and the decoder tries to build a sequence by those given features. The first model that we tried we develop was the convolutional recurrent neural network. As its name indicates, it's a combination of convolutional layers and recurrent layers. This model was developed first for scene text recognition, and we thought that it can be performed very well on this scenario. This model also was the first one we developed, so our first idea was to have a lightweight model. So that's the reason this model uses as an input image 160 input image sizes of 160 by 40. In this case, we remove the convolutional stride layers by using max pool. And for the decoder part, it's a bidirectional ELSTM layer that works perfectly for this scenario. The other model that we developed after all was the multitask learning model. It's basically called like this, given that each digit of the sequence is modeled as a task on the network. This model uses the well-known BGG16 architecture as the feature extractor, and therefore it requires more larger images. In this case, we are using image size of 288 by 60. And for the decoder, we use two convolutional layers, but in this case, they have one dimension. So moving on, to train these models, we basically have one of the challenges that we have for this project was basically that all the water meters are protected by GDPR laws. So it was quite hard to find open datasets that are available to the public and that contain thousands of images. Most of the cases that we found on the literature are images with a low amount of images, or with images that doesn't have the correct length that we were looking for. So that's the reason we decided to go for this Russian water meters. It's basically a dataset that was crowded from the Yandex Toloka platform, and it is hosted on Kaggle, so it's free to everybody. This dataset has 1,200 images with exactly one counter in each of the images, and this counter has a length of 8 digits. Examples of these water meters can be seen on this on the right image. And something that was interesting to us, given that this is a free open dataset that was not published anywhere, we decided to see if those water meters are real, coming from the in situ uses, so that if they were actually used by people. So we simply pass a check on the frequency distribution of the digits, and we saw that all the digits follow the Benford laws, telling us that the distribution of the digits flows naturally. Once that we have our model set, we use these metrics to train them. Basically, the Roy detector model uses a loss that is a combination of focal and dice loss. And for the predictors, we use the connectionist temporal classification that basically help us to reconstruct the sequence and calculate the loss. And for the multitask model, we treat it as a classification one for each digit, so we use the categorical cross entropy. As the evaluation metrics, we use the well-known intersection over union just to help us see if we are going into the good direction. For the second predictors, we make use of the Levenstein distance that tell us how erroneous our predictor sequences are. So once we have all our models set up, we needed to perform some pre-processing steps. As you may know, nowadays deep learning models require a lot of amount of images, or in this case. So as we only have a data set with 1,200, we require to perform some data augmentation techniques. For the raw detector model, you can see on this image that the images were shift, scaled, and rotated. And in some cases, also the coloration was changed. We also add some blurring and add some contrast, and always taking care that the mask, that the counter area is within the image, as you can see in these examples. Regarding the sequence predictor models, we also perform some data techniques. You can see here the original image that were cropped from the counter, from the actual water meter. And in this case, we also change some blurring, and we add some rotation to increase the level of difficulty for the model. Something important to note is that this Russian dataset was provided also with the targets, but the targets come with the targets in fact were only provide sensitive information. What I'm trying to say is that in this example, the 00026, those 3 zeros were deleted from the actual target, giving us some instability when we were training the model, as the model were not able to predict these digits on the left side. Given as these occur sometimes on the right side, we needed to also perform padding for the sequence targets on the left and on the right. So basically, this gives us an infrequency where you can see that all the numbers are right now correctly aligned. With this, our trainings were passing more smoothly. So now I'm going to talk about some quantitative results. As we can see, or you may already saw this, the raw detector model takes 3 hours to train, basically. This is because they're trying to reconstruct images of 720 by 720. Those images are quite large, very important for our sequence predictor models. Therefore, it requires more time for the training. All the models were trained until they reach some convergence. Something to note is that despite the great loss on the CRNN model, the integer accuracy remains quite high for both of the models. Now I'm going to present some qualitative results. In this image, we can see how the raw detector model actually successfully predicts the counter area. But sometimes, given the illumination or the rotation of the image, it produces some. It's not able to successfully predict the entire counter area. In this case, yes. In this case, also this area was mispredicted, given that if you see correctly, this image is a 3-0. On the other hand, this raw detector model also was applied to gas meter images, and we can see that, in fact, if the image is horizontally aligned, it really the model can really provide good results. But nevertheless, sometimes as this counter area change the coloration comparing with the gas meters, so it really confuses sometimes the raw detector model. Continue with the sequence predictors. We can see here the prediction of the counter, and this is exactly what we were looking for when creating these models. the sequences are correct, are well predicted. And sometimes the model suffers from some, how to say, weak, weak, some, it confuses sometimes the digits. As you can see, this 0 is confused by an 8. This could be to the round nature of the number, probably. Or sometimes it confuses the 1 to the 7th. This is a 7, but it predicts a 1. And the 6 still confused by a 9. This is not always the case, as the qualitative analysis showed that our interaccuracy is quite high. So sometimes the model is not successfully can produce these results. So now the portability analysis. One of the important questions that one of the important requirements that we have in this project was the portability of the models, as we needed to put it on mobile devices. We use TensorFlow Lite to perform the portable conversion. All the analysis here was performed on a Colab platform. And basically, we can say that the models, the required storage of the different models are between 8 megabytes and 170 megabytes for the multitask. Those models are, this last model is still huge one, but still can be ported into a mobile. And regarding the memory consumption, it fluctuates between 600 and 700 for the CNN model, and for the multitask model between 600 and 1 gigabyte of memory, basically. What we're trying to say is that those numbers are still within the limits of the mobile device capability. Overall, when we combine all our solutions, we can see that the integer accuracy suffer a substantial drawback. This is explained as the Roy detector model sometimes fails to really capture the entire counter area. So it leads to a wrong prediction of the CNN model. Nevertheless, the accuracy values are still quite high, and the Levenshtein eddy distance tell us that overall there is at least one digit that is wrongly predicted. So, in conclusion, this project basically what they tell us is that pre-processing the images and targets, it really can lead to an improvement of the results. We presented two models for prediction of the counter, just as a test. Our Roy detector models, and sequence predictor models can really perform within the mobile capabilities. And all this project was already done and presented to delivered to the NRB group, especially to the data science and AI solutions section.
So if I just may add, the aim is to create an application that can run on a mobile device, on a mobile phone, such that an employee can simply download this application and then read a water meter value using his or her mobile phone directly. And our application would then be able to detect the different digits in the actual physical water meter and recognize those digits accordingly. As my colleague has shown in his previous slides, the main cause of errors is the fact that some digits do look similar, like 0 and 8, or 1 and 7. And also a different cause of error, which occurs in the decimal part, is that sometimes numbers switch. So the number is stuck between two values, 7 and 8, for instance. And in those particular situations, then obviously our algorithms is also confused. But the main deliverable here was a lightweight, quite sophisticated AI algorithm for accurately recognizing digits, despite the fact that those digits appearing in the water meter were sometimes very blurred or when in very awkward positions or were grayed out. So it's a robust, lightweight solution that can be ported to mobile devices.
Yeah, so thank you very much for giving us the opportunity to show you what we have been doing on the FlexWatter project. So it's a project that has been started 1 year ago, and here, of course, we don't have yet finished this project, but I will show you here what is really the objective of the project and what we have achieved so far. So when we think about water and electricity, usually we know that they are usually not very good friends. And in fact, it's a pity, because here the project was really to see how we could use water infrastructure, and in particular water distribution and water transport, in order to support electrical transmission network. This project is a 4-year project that has been awarded by the national, I don't know how you call that, but it's Service Public Fédéral Économie. So it's really the part that was busy with energy transition. And this project was selected among quite a few projects in order to solve the challenge of energy transition. As you know, there will be some future challenge regarding integration of renewable energy, and the fact that we will stop as well some very important sources of electrical energy, like nuclear power. This project has been set up together with different partners. So we have Vivaqua, which is the distributor of drinkable water. He provides us the data and as well the use case, so that we can work on real situation in this project. We have also as partner the University of Brussels, because we were as well thinking about a new pumping system that could be valuable as well in this context. We have ISET, which is a kind of research center, which is the project lead and responsible for coordination, as well for technical matters regarding optimization. And we have as well the University of Liège that will be designing a kind of mini pumping system in the lab using first principle model, and basically it will be very useful as well to test some control model on the system without going really on the real system, because we need, of course, to have a kind of test bench in order to be sure that what we do does make sense. And we have as well the University of Ghent that they will assess as well renewable source integration and electrical storage in the distribution network of water. And us, we are responsible on the AI topic and bringing as well our industrial expertise in how to deliver a smart EMS system in this context. If we think about the problem now, of course, the increasing challenge in the electrical power system is the fact that you need always to balance demand of energy with production of energy. And that's a big challenge, because when you increase the part of renewable energy, you increase as well the level of uncertainty. And then it becomes really difficult to balance the consumption of energy with the production of energy. And for the system operator, which is in Belgium, Elia, that starts to be a bit hard to manage the system as well. And I don't know if you heard that in the news, but in January this year, we almost had a blackout in Europe. And in fact, they had to split Europe in two in order to be sure that the system could be safe in terms of supply of electricity. So the idea of this project is to basically try to see how the flexibility that you have in the water distribution system could help in balancing the demand and the production of energy. And you have in fact different sources, because when you are looking at a water distribution system, you have big pumps, so they are consuming electrical energy. So you can decide at a certain time maybe to not start the pump, but you have as well water that are stored, and it's a kind of potential energy that you could use at different time as well, either to produce electricity or to use at different in a different way in order to distribute the water during your on the pipe of your water system. So that's basically the idea, is to try to see how we could better synchronize the water system with the electrical system, and by combining both, we could create as well some interesting situation where we could save energy cost on the side of the water system, and then improve the reliability of the electrical grid system. So how do we do this? The first thing is that from the pure data point of view, I won't go, of course, in the other topics that are not really related to the data, but I will talk you more on the data system. When you manage a water system, you have plenty of data available. You have, of course, all the hydraulic data that is provided here by the system, by the water system operator, which is Vivaqua. So it's the flow of water, it's the electricity consumption of the pumps. So they have really a lot of data regarding the operation of the system. Then you have the weather data, which is also a quite important system as well, a quite important source of information as well, because it has an impact, of course, on the balance of the electrical system, because if you have a lot of sun and a lot of wind, you will have a lot of excess in the term of energy available in the electrical grid. So it's important to know that as well. And in the same time, if you know that it will rain a lot, it's also important to know that, because you will manage the water system differently. So weather data and forecast of weather data is extremely important. Then you have the electrical network data, which basically ELIA in Belgium. So they provide now a lot of information on the current situation of the grid and past situation of the grid. And you have as well electrical market data. So what is the price of electricity? On the spot market, the price is updated every 15 hours. So you need as well to include this kind of information so that you can really optimize a decision based on this price signal as well. So the first thing that we have to do there is to build a reliable predictive model, and that's the first part where artificial intelligence will be used to build predictive model so that we can better predict water consumption, but in the same time better predict as well the electrical imbalance that we have on the power network. And of course, these predictive models should be very useful as well, because as soon as you have, I talk about maybe installing on the system a solar panel, that's also very important to predict what would be the production of this solar panel at least one day ahead. And this is really what we have been doing in the very beginning of the project, collecting the data and starting to build a predictive model. But predicting is not enough. You need as well to optimize your decision. And basically optimize the decision in a water system is basically to change the schedule of the pumping of the water from the water well, or even the production of the water coming from rivers, right? Because they have plants that are producing drinkable water by pumping water from the plant. So you need really to incorporate all the parameters that you can manipulate in order to optimize this asset, because you don't, when you are pumping water, you don't pump water so that it's automatically available at your home, right? You pump water so that you can store this water, and the storage of water will then feed naturally all the distribution network up to your home and up to the final consumer. So that's really where artificial intelligence is really important in this project, because we have a massive amount of data collected, and it's extremely hard to build model from scratch. So you need really the help of artificial intelligence, and it's specifically machine learning, to learn how the system behaves and how to optimize this system as well. Well, building the model is also a very easy part, I would say. The most challenging part is how to deploy it in real time, because and that's really a topic that is emerging, I think, everywhere, that you might have heard quite a lot about machine learning ops or AI ops. And this is, in fact, translate the fact that doing pilot project and doing model using artificial intelligence is not very difficult, in fact. The problem that you have is how do you scale the system so that you can update the model automatically, and that you can integrate this model in the current decision process of the system. So in this case, as I explained in the slide before, you have different sources of information. You have the DCS system. So the DCS system are basically where you have all the sensor data at Vivaqua, and this provide a useful amount of information that will accumulate with time. And then you have all the market information, weather data, and some information might be available in the future, and not now. So for example, Vivaqua might decide to invest in new pumps. They might decide as well at Elia to provide new type of data. On the market level, you might have as well new type of product available. So you need to be very robust regarding that, so that the model that we develop and the EMS, or the energy management system that we develop, is robust enough so that the system can be really useful in the long term. So we are using different components to do that. There is, of course, the requirement to collect automatically and continuously data, to merge this whole data set in a data lake, and then this data lake would stream an analytics and a machine learning platform. In this case, we are using our platform to do that, so that the model that we build there can be updated and use real time to feed dashboards, so that operators can decide what to do. And in a second's time, they can automatically send signal to the pumps and decide what would be the desired output of the pump, so that we optimize the whole system, right? So that's really the second challenge that we have here. Once we have built the model, being sure that the model that we build will be sustainable and will be robust, given the fact that the environment will probably change in the future. So to give you a flavor of result that we got in this project, this is, for example, model that we build, and we used for that neural network and ensemble methods to predict basically the requirement, the demand of water. So this is, of course, very important to have that, because one day ahead, you need to know exactly what would be the consumption of water, so that you can better schedule the pumps and deliver the right amount of water into the system. And of course, it's also very important to understand what are the main factors that are influencing this water consumption. So of course, here you see that you have 3 parameters that can be quite understandable. Time is playing an important factor. The day of the week, you can guess that during the week or during the weekend, you don't have the same pattern of energy consumption, because I mean you have a lot of companies that are not working during the weekend, and you have as well the weather that can play an important role as well, because if you might consume more water if it's warmer. right? So it's an example of models that we are currently building in this project. Now, in terms of prescription, so what the system is doing, you see that here, the pump profile in blue, this is what is currently done by Vivaqua. By using optimization, you see that the red curve here, it's a completely different profile, because this profile takes into account the whole data that I talked before. And this is, of course, a big challenge as well for Vivaqua, because they need to change the way they operate the pump as well, right? So that's quite interesting to see that by doing this change in the set schedule of the plant, we are still able to meet the demand of water consumption. And in the same time, if we calculate here the cost, so specific cost, so what does it cost to produce or to distribute this amount of water, you see that we have a pretty different shape. You see that there is more volatility. And at the end, we have calculated that if we can use a balancing market as well, we would be able to save 25% of the cost of the water distribution. So you see that this kind of system can quite quickly bring interesting benefits, first to the water utility that distribute the water, and in the same time contribute in a positive way by replying in an adequate way to the signal of the market of the energy system as well, right? And so that's really where we stand right now. The challenge that we have, of course, is to be sure that the system is robust enough, and as well to change the way the system is currently operated by operators. So there are still quite a lot of things that we have to deal with into this project, but the very early result that I share with you here seems to be extremely promising.
Today, I'll be talking about how AI can have a positive impact on the availability of essential resources. But more specifically, a leak detection algorithm we built for the water group. So this will be the agenda of today. So first, we start with a small introduction about the context of the case, why we're doing it. Then secondly, we'll be talking about data engineering part of the project. Thirdly, we'll be talking about data science, well, the model that we've built. And lastly, there will be some time for some questions. So first, water data management in Flanders. In general, water is a scarce resource, but it's only just beginning. Research has shown that the global water crisis will be there by 2040 if we don't do anything. And if we zoom in on Belgium, we can actually really see that we're at a big risk of withdrawing from supply. So why is that in Belgium? Because we're very dependent on groundwater, and groundwater is a non-renewable source. So if it doesn't rain enough, we'll be out of water. Next to that, leaks also cause damage. So when a leak occurs, it's possible that it infects the water pipes and that it really affects the global water quality. Next to that, you can also have things like sinkholes, which cause a lot of damage and that cost so much to repair. So sometimes it's very important to really react quickly when a leak occurs. And also in general, a study has shown that the reliability of the water supply network really affects things like migration, because if you can't rely on water, then some people decide to move. So it also has a very big economical impact. Now, specific for Europe, we know that almost 23% of all produced water in Europe is not consumed. Not consumed does not mean in this case that it's all due to leaks, but a very big part of it is due to leaks. Another part can be water theft or the fire department using it, and this is not invoiced, and that is actually the KPI that we're trying to optimize, the non-revenue water. which is calculated by subtracting the billed water from the consumed water and dividing it by the consumed water. Now, the water group, the customer. So the water group, as you can see here on the map, provides water to almost 3 million customers in Flanders. It does this through a pipe network of more than 33,000 kilometers, which is actually one of the biggest in the world. And the goal of the project here is to minimize water waste by detecting leaks earlier and intervening at the right time. So a pipe network of 33,000 kilometers. This really entails in a lot of costs to maintain it. And it is very hard to maintain this entire network of pipes. So field engineers, when leaks occur, they go looking for leaks. Water is scarce, so we really have to protect it. But at the same time, it's also very expensive to send field engineers actually in the field. Sometimes it can take up to 3 weeks to sweep a DMA for leaks without big results. So it's a very expensive process. So it is very important to find the right balance between when you actually intervene and when you don't. So it is because of that we're going to try to use data and artificial intelligence to prioritize the areas with most potential for water loss, to really get a bang for our buck. So, of course, you cannot build an algorithm without data. And I'm sure that most of you have already heard this, but in any data science project, it's usually about 80% data preparation. And in this case, it was the same. So the first part, we have to get data from all different sources and really put them at the same scale. We integrate them and we load them in our data lake. We process them, we clean them, then we apply our algorithm, and then we provide the results to the customer. It is only here that the algorithm is actually applied. For this so coding an algorithm is really not equal, as Philippe already mentioned, to deploying an algorithm in production at scale. And to give you a bit of a feel for it, we spent 20 days on actually developing the algorithm. We spent 50 days on prototyping a tool to analyze the different results that we generate. We spent 150 days on the actual industrial implementation and building a full-blown integrated application. But first, how is the data collected? So the way that most water companies actually try to measure the amount of water that is consumed is by applying the technique which is called district metered area. These, as you can see, are all small clusters of water users. So you can really monitor all the users that are using water in here. One thing that is very important here is that it's a secluded hole. So it should always be isolated by meters to measure the full in and outflow of DMA. Because it's only by doing that that you can actually see how much water is being consumed in each area. For the case of the water group, the entire region is divided in 407 different DMAs. They're stored in 5 different databases because of historical growth. And all the data is originating from more than 900 plus sensors. If we do it correctly, usually water consumption really looks like this, with always going back to the lowest point and with the most stable point being in the night. And so, as already mentioned, not all data comes from the same source. And this has been, well, to not say it nicely, a bitch to really tackle. Because you have 5 different data structures, 5 different ways of registering the data, 5 different timescales. So the first thing you have to do, the frequency. So you have to put them on the same scale that you can actually use the data from all different databases for the same DMAs. Next to that, also, we have a lot of historical sensors there. Some of them are already older than 20 years. And it's because of that not all the data sends at the same time. So some sends every minute, some every hour, some only every day, and even some are only manually registered every month. And next to that, devices can also be changed, and so you have to really solve that problem to make a history that is continuous. Next to that, data quality is always at the center in any data science project, and it wasn't different in this case, because most of the issues that we actually experienced with detecting leaks was due to bad quality of data. So, for example, low precision in measurements result in low precision of the algorithm. And if we look at this, you can clearly see this is a DMA with quite a good precision, and you can clearly see that this is going to be way easier to detect leaks on than here, because here you're constantly going to detect shifts because it just jumps from one unit to the other. Next complexity is big data, because, well, deploying an algorithm at scale is not possible with a Jupyter notebook and a few CSV or Excel files. We need to collect all the data, history going from 2010, and we need to store this data. For this, we use an Azure Data Lake storage. Then, of course, because we're dealing with big data, we need fast computations to be able to detect leaks fast enough. So for big data, we require big computations, and we use Spark for that. And then accessibility, since we're working on this with quite a big team, we're using Databricks to collaborate and to develop together. But one thing you can never forget with data science, and it is often overlooked, it is often the hardest part to really convince the end user of using your applications. These people have been used to a certain way of working for 20 years. And when you come with a project like this, you really have to make it visually and attractive and really train your users so they know exactly how they can interpret every leak or result that is generated and do it in a visually attractive way. To facilitate this, we went from a very simple prototype architecture where we just had one virtual machine with both R and SQL on it. We had to evolve to a fully blown integrated application. And doing this really made it way more complex to set up everything. You have to deal with security, real-time application, building a custom front end on it, and way more. Then the next part is data science. So the leak detection using Bayesian modeling. So first, we have to start with how can we define a leak. Generally, it's always the same thing. We have a certain volume level and you sample data every day. What you try to do is you try to, let's say that this is a normal water usage at this time. What we try to do is we try to fit a certain mean with a t-distribution with a certain variance. Then at some point, something changes in the volume levels. And then we see that actually the same variance appears again on the other side of the volume shift, but with a different mean. So here we can actually see that the difference between both detected means is actually the size of the leak. So the assumption that we made here actually, and we also saw in the data, was that we expect the variance to be constant before and after the leak. Also, we retrain this variance every time we sample. So over time, the variance will get more accurate and really be able to detect smaller leaks as well. Also, finally, because the people that actually, the field engineers actually don't have the capacity of constantly changing where they're looking for leaks, we decided to focus on the night data as the variance is the lowest there, and so it's the most accurate to actually detect leaks. Otherwise, you would always get false alarms, and since there's limited capacity of actually looking for leaks, it wouldn't be very productive. So the parameters of this model are the mean water consumption in non-leak situation, the size of the leak, the variance, and the time of leak occurrence. These are all the parameters that we try to estimate. The model is defined by a t-distribution over these parameters, and to sample for these parameters, we actually used Bayesian statistics, and more specifically the RJAX package within R. So to conclude then, we start with the water consumption. The first thing we do is we're only going to focus on the nightly consumption. As we can clearly see, the variance is way more stable here. Then we try to fit a model with a constant, with a certain mean, and for every data point we sample more, we estimate the probability of the presence of either one volume level with a mean, a variance, and a mean and a variance and a leak, or the probability of it just being one mean with one variance. We estimate this presence of a leak every time we sample new data. Once the threshold is passed, then we set a volume shift. And this is the basis for all the later calculations. This doesn't necessarily mean that there's a leak, but it really accurately samples the average night consumption, and we can really use that further down to alert the field engineers. So when do we notify the field engineer? So let's say, for example, you can clearly see the different shifts in volume level here, and currently we're at this volume level. This, looking back, really looks like something is happening here. So what do? We check the new shift and we compare it to all the previous shifts. Then we calculate the probability of this current blue line, or this current sampled average volume, and we compare it to all the previous shifts. If it exceeds a certain threshold, then we send out an alert that something very rare is happening in the water network, and that you should actually react on it as fast as you can. Next to that, we also try to prioritize over all the 407 different zones. And we do that by also checking the current volume level, and we calculate the difference between the current volume level and the baseline. We assume that the baseline, for that we take the median of all sampled volume levels, and we put that as a very robust center of your measurements. And you could actually think that that should be the normal situations. It's only in certain situations where it's more than 50% of the time in leak situation where this is estimated pretty poorly. Then we compare that to the current volume level, so the currently active level of shift, and then we calculate this distance. If we then rank all the DMAs over this distance, we can actually see which DMAs have the most potential water loss, and we start by focusing on those DMAs. And that was it.